So let's just go ahead and start off with your background. Maybe tell us a little bit about yourself.
Yeah, for sure. So I'm Jeffrey. I'm a third year PhD student at Harvard, advised by VJ Reddy. Loosely, my interests span research-wise machine learning and systems. So on one side, I'm interested in kind of large-scale machine learning. How do we make it robust, stable, scalable? And on the other side, I'm super interested in how we can use machine learning to actually make systems better. Right now, a lot of work in like the code AI space and kind of how to automate performance engineering. But I think there's a lot more we can do to kind of make these super useful foundation models actually useful for kind of like a lot of systems level tests.
Awesome. So maybe tell us a little bit about how you first got interested in kind of computer science and research more broadly, and then kind of what drove you to, kind of end up, pursuing the PhD path.
Yeah, for sure. So I grew up in the Bay Area. I was born in San Jose, and so I think being that close to Silicon Valley is like probably the easiest way to get in CS. But I think just as a kid, I got super interested in just programming in general. I remember this is gonna sound like a Bay Area meme, but like I think my mom, remember in middle school was doing job interviews, so she'd have that green like cracking coding interview book. And so sometimes over lunch or over dinner or something, we would just like chat about some questions. I kind of didn't get through any of them as a kid, but kind of like slowly over time, you kind of start seeing like algorithmic patterns, and so I think that's how I really got into CS. I think like I really enjoyed kind of how computer science has like stuff like solving problems at scale as like a first order priority. I think a lot of the computer science problems like scalability is the hardest challenge to figure out, and so I think that's how I've gotten super into CS. I think like as I've gone through the years, kind of my interests have like kind of jumped all over the place, but definitely I think that's how I first got into things.
Awesome. And so I guess, you ended up, going to Caltech for undergrad, and there, you were kind of, studying computer science, you kind of double majored in finance as well. You minored in data science. So I guess maybe just kind of tell us a little bit about kind of your thought process at Caltech. And I guess, critically, you interned at Citadel kind of, I think, your final summer, and then you ended up working full time at Citadel. So maybe just tell us a little bit about kind of that thought process and, maybe more broadly, how you kind of made that decision to leave Citadel and go off and get a PhD.
Yeah, for sure. I think so. The reason why I decided to kind of double major at Caltech, I think Caltech has this like very common two majors that have really high synergy. One is computer science, the other one is BEM, which is basically finance. But I think one of the things I really wanted to get into when I got into Caltech is like I think understanding the technical is like super important. So like the CS degree was super important, but I think understanding kind of all the other sides as well. I think I took some like really cool like venture capital slash like risk management courses. One of my favorite classes from undergrad still is this course I took with a professor on option pricing theory, and I think a lot of like the theory and the proofs were like super elegant, like proof by arbitrage. But I think like the reason why kind of like that finance double major got me interested in kind of a lot of other fields, including kind of the internship I did at Citadel, and then eventually going there full time for a year. So that's kind of how I got there. I think the year that I was at Citadel was super fun. I worked in the fixed income business at Citadel. Super fun challenges, super lean team. I think like got a lot of responsibility really quickly. But I think during that year, I kind of spent that year. I did some research in undergrad, but I kind of spent that year out of research, and I think that year is when like ChatGPT really took off. I think like 3.5 came out that year, and so even at the company, we were thinking about how to use it and like kind of those space of things. And so in my mind, it definitely felt like, oh, maybe kind of going back to grad school would be a good idea. And kind of, I'm super happy now, kind of like getting much closer to the AI research side of things. But that's kind of how my thought process jumped from undergrad to working to back to the PhD.
Awesome. Like, when you were at Caltech, you worked with, I guess you were in kind of the tensor lab, and you kind of worked on like, generalizing competitive gradient descent methods to multi-agent RL settings, things like this. I guess like how did you kind of decide what you wanted to focus your PhD on? Like, was that something that kind of naturally branched off from undergrad? Like, what did that kind of decision process look like?
Yeah, for sure. So I think the things I was involved in undergrad. So research wise, I think this like competitive gradient methods, one of the really interesting things, it's basically kind of leveraging how do you leverage like maybe like gradient descent is first order. How do you leverage like maybe higher order or like first order with respect to multiple agents? How do you leverage that for like better optimization methods? I think within that, there's like a pretty interesting ways to implement it. Basically, kind of some of these methods require like Hessian matrix invertibility, which is not really possible. And so there's a lot of efficient methods like conjugate gradient or a lot of these iterative methods that kind of more efficiently compute machine learning. And so that's kind of how I got super interested in a lot of like this ML systems work is because kind of how you define an algorithm in theory kind of doesn't match how it's actually implemented. And then kind of other things I was involved in undergrad. I had TA'd for Caltech's core computing systems course. And so it was a course focused on memory organization, computer arithmetic, kind of starting from the low level of the stack. So like x86 assembly, going all the way up to like stuff like garbage collection or like reproducing like Intel's like system or Intel's like meltdown exploit to kind of even more high level system things. And so kind of that TA experience also let me capture like the full level of the stack. And so I think marrying those two things with machine learning and systems kind of shaped a lot of like my research interests now.
Hmm. Awesome. And kind of tell us a little bit about your time at Harvard. So you are now advised by, Professor Vijay Janapa Reddy, as you kind of talked about. You, as you sort of mentioned, you're now a third year. Tell us a little bit about kind of your first few years. What were some of the things you learned? What did kind of that journey look like? And what's kind of your outlook on maybe some of the things you want to, kind of tackle in the next few years?
Yeah, for sure. So yeah, definitely kind of going back to the PhD was for sure an adjustment. I think coming from industry, going from undergrad to industry, and then coming back and kind of getting back to the school environment was for sure an adjustment. I think even before I came back to the PhD, I remember telling VJ how I really wanted to work on language models for code, or just the idea that like I think maybe we could program things in something other than like C++ or whatnot. And I think back then, I remember my first year, we'd worked on some like kind of optimizing some retrieval augmented generation stuff for code. But back then, I think models were way worse. Like I remember, I think SWE-bench actually was published like maybe midway through my first semester, and kind of state of the art was like 1%, and now models are like to where they are. So I feel like kind of this like growth in like coding agents and how good foundation models are over code has kind of mirrored a lot of my PhD so far. So it's like really cool to see the capabilities grow. I think with that, like having seen kind of where they were to where they are now, it kind of makes me super excited about kind of like what can they do further, and like specifically, can they reason over code better? What are the challenges? What's holding them back? And like anything in that space of things.
Mhm. Awesome. So maybe we can go ahead and kind of jump into some of your papers here. You had a paper titled Fed Stalemate, Buffered Asynchronous Federated Learning with Fair Aggregation via Staleness Reweighting. So this was back in kind of like June 2024, and was a collaboration with a bunch of other really awesome people, Alan Tu, Yiling Chen, and obviously your advisor, VJ. Tell us a little bit about kind of some of this work, and this is obviously maybe a little bit more related to federated learning. Is this kind of still related to kind of some of your core research interests? What kind of was the motivation for this paper?
Yeah, for sure. So that one started as so I think Yiling was Professor Chen or Yiling was teaching a class on I think econ CS or just kind of like just economics and CS and multi-agent systems, and then of one of them kind of the tie to ML is like federated learning is a case where kind of you have multi-agent systems interacting. And so one big thing, like I had no experience with federated learning before, and so I kind of started doing some reading. It sounds super cool, just like kind of coordinating multiple agents to kind of train on different subset of data. You maintain some kind of privacy. I naturally you see kind of like issues with just doing synchronicity. Basically, in federated learning, if you wait for the slowest agent every round, kind of you're affecting your throughput. And so I think Alan and I started looking into things like asynchronous federated learning. And then there's this one really cool paper from the folks at Facebook, I think FedBuff, which looked at kind of like, oh, actually, let's just have agents populate a buffer with updates, and this turns out to work pretty well in practice and kind of really improve throughput. Because the class was like econ themed, I think one thing we realized was um, kind of if you were an agent that produces updates really really fast, kind of the model you can bias the model towards you much more heavily, right? And so kind of because this is like a game theory type approach, we were wondering, are there ways to kind of reduce that bias towards fast performing agents, but without doing it in a way such that kind of there is some strategic manipulation possible. And so this is kind of a nod to kind of some of my previous interests with game theory. But basically, we came up with a method that I think achieves strategy proofness with enough agents, in the sense that basically agents do want to report their updates, report a truthful update, and not try and slow down the reporting speed in a way that tries to get the model to bias towards them. In terms of how this shapes some of my future interests, I don't really work on federated learning anymore, but
Mm-hmm.
it turns out kind of a lot of these learnings are super timeless for stuff like kind of large scale training. Like federated learning is actually just roughly data parallelism, right? And so actually, I think in terms of how this shapes some like future opportunities, I think actually some of the folks I ended up interning with at Amazon, this came up kind of like during our interview discussion, just because they had seen kind of this background with this kind of federated learning and how that applies to kind of like how they think about distributed learning. So
Mm-hmm. Awesome. And kind of like getting to your time at AWS, you ended up working on a paper titled Understanding Silent Data Corruption in LLM Training. And I think this was kind of part of your time at AWS. So maybe tell us a little bit about this.
Yeah, for sure. Yeah, so my time at AWS, I think the team that I worked on focused on kind of just fault resiliency at scale. I think one big thing with these like foundation model training jobs as they're getting more and more expensive is that kind of more and more resources are need to be dedicated to like making sure training runs don't crash. And even when they don't crash, that like you're actually learning what you're supposed to. And so anecdotally, I think what a bunch of researchers found kind of once they started allocating hardware to these big runs is that they'd see kind of very mysterious like training run crashes. They just see big loss spikes. These trains are generally in deterministic mode, and so when you replay those kind of training runs or those batches of data, kind of those spikes disappear. And so this points to things, this like phenomena called silent data corruption, where kind of hardware just errantly makes incorrect computations, but they don't propagate into loud errors to the user. And so kind of what my project was that summer, and then kind of the paper that we ended up publishing was to explore kind of how one is like, can we characterize what's going on? Like a lot of the times we only see the loud errors, like all these like foundation model technical reports show kind of like the loud errors where it interrupts training, but can we characterize what's happening at like a sub-model training level? So specifically, we characterized that kind of like how often are the outputs of a transformer in the forward and backward not matching, how often are kind of gradients not matching, and then how eventually, if you don't correct these errors at all, kind of how much do models actually diverge? And then qualitatively, with some like fine tuning experiments, kind of how differently can they actually perform?
Mhm. Awesome. And kind of, I think after your time at AWS, you started kind of being a student researcher at Google. You kind of focused on kind of LMs for code, which maybe gets us a little bit closer to some of your current interests. And I think, you kind of like studied, how to improve multi-step reasoning. And I think you kind of worked on things like, optimizing code at scale with Milad Hashemi as well, and maybe Amir as well. So maybe tell us a little bit about your interests and some of the work that you were doing at Google to the extent that you're kind of able to talk about.
Yeah, for sure. Yeah, I can't talk too much about the internal work, but kind
Yeah.
of the team that I was working on at Google was focusing on the team was called like Learn to Perf. Specifically, I think the team is oriented around how do we use machine learning to kind of improve compute efficiency for like Google's scale of compute, right? I think one big thing is that we're training these models to be like so useful and kind of like have this advanced reasoning. It'd be really cool if we could also train them to like also kind of save some money in terms of like large scale compute. And so kind of that's the general theme of the group. We worked on some like fun projects internally that I unfortunately can't talk about on the podcast. But I think one of the big things that what came out of it was kind of we also wanted to like publish a benchmark just to get people more excited in this area. I think by when I started working with the group, I think SWE-bench was started to get maybe like the 40 to 60% score range, but kind of we didn't see too many benchmarks that were looking at like performance optimization. I think that's something that the systems community cares about and like figuring out if models can do this task is pretty important. And so kind of that's the motivation from the internal work to kind of externalizing kind of an artifact, something for the community to get excited about.
Amazing. And all of this finally brings us to SWE-efficiency, which we're about to dig into a lot more depth. So maybe just like let's start off with kind of, I mean, I think you kind of have already highlighted the motivation of kind of what you were working on. Maybe tell us a little about the story. So, you join, Google, you kind of have this interest in, working on kind of like AI for code. You have this interest in like, okay, performance optimization. This is a project that you want to work on. Kind of tell us a little bit about kind of the motivation for this paper, and kind of that journey.
Yeah, for sure. So I think a big motivation for the paper comes down to like the what versus the how of code. I think up until kind of when we started working on this, the what is pretty clear. We had a lot of benchmarks that human eval apps that look at kind of given specification and some tests, can I write a function that implements it, right? So new code behavior. I think until kind of like when we started working on this, there weren't a lot of benchmarks that tested the how, which is like, okay, given some existing code, could we rewrite to be better? There's so many different other hows that I think would be really cool to explore in the future, but kind of performance is a really big one, right? And so kind of when we started working on this project, the how was pretty interesting. I think the I started looking at like kind of like existing code stuff like SWE-bench, which has obviously done like so much really cool work for the community and kind of getting people excited about coding agents. But kind of like some actually interesting bits kind of popped out in terms of what we realized kind of like SWE-bench might have been missing, or kind of like its data set collection pipeline kind of results in. One big one is kind of This is getting into a little of the nitty gritty, but kind of SWE-bench selects pull requests as for their base tasks that actually contribute tests. So kind of they use this new test coverage, or they use these new tests to actually cover the existing behavior or the behavior that they add in the PR. And so kind of this is great for kind of testing bug fix level stuff. But what we found is kind of looking at a lot of these GitHub PRs is that when people make performance changes, oftentimes they don't add tests. This is like a pretty fundamental bit behind like test-driven development in the sense that if you add new behavior, you add unit tests, but performance changes aren't really new behavior. And so kind of we designed our SWE-efficiency pipeline to kind of like invert this criteria, and then we have a bunch of other interesting stuff on top just to make sure we're selecting like reproducible, verifiable, and like really high quality instances. But kind of this was like one of the big motivations and like seeing kind of a gap in SWE-bench and then designing SWE-efficiency to kind of fill in this next gap and kind of evaluate a different facet of software engineering or performance engineering.
Awesome. So I guess maybe tell us a little about, I mean, I feel like, you know, definitely kind of the ML systems folks in the audience will know a lot more about performance engineering. But for people who maybe aren't familiar with performance engineering, maybe just kind of give us a little bit of kind of like the bare bones of the motivation of like how performance engineering differs from software engineering, and maybe kind of like what those fundamental kind of like from first principles, like how are they different, and like how does, I think you've already kind of highlighted this a little bit. Maybe tell us a little bit more about how their difference kind of informs kind of the difference between SWE-efficiency and say SWE-bench.
Yeah, for sure. I think the one of the key differences I'd say between performance engineering and software engineering, I think, is the idea of like just like the core idea of verification. I think in my mind, the way that I've always organized performance engineering is kind of in three steps. One is kind of given some kind of workload, something about it is suboptimal. So you want to kind of diagnose, figure out what the bottleneck is. And so that's kind of like the first stage, just like localizing kind of where the performance problem is. The second step is like intervention. So once I know where this bottleneck is, now I actually need to implement things. I think intervention is kind of how I imagine stuff like maybe SWE-bench like kind of tests more. The idea that like kind of not only you do have to localize a change, but kind of implementing something algorithmically is kind of like the focus there, right? And so in performance engineering, you do have to edit and update code too. But kind of this stage is where you have to like reason algorithmically about things and kind of rewrite in a more optimal way. And then the last step that I think kind of maybe is not just in native software engineering, but the last step I think is to the like verifying that no new behavior actually happens. I think this is like a pretty big one. This is I think one of the reasons why SWE efficiency is pretty hard in the sense that kind of agents need to not only do they need to know how to make the edit, but they also need to know kind of like where to find the tests and how to check that their edit went through correctly. I think it's becoming super clear that agents are like really good at just kind of feedback driven optimization on a single objective. But kind of one of the things that it turns out human software developers are really good at doing is that when they make a change, they kind of understand how their change impacts the rest of the code base. I think this is something that I think SWE-efficiency tries to evaluate for code agents and something that's kind of a room for improvement for both people who post train models as well as people who design harnesses. What was the second part of kind of what you were asking?
Yeah, I mean, I think that's great. I think we can kind of start to get into the results actually. Like, I think one thing that's really kind of interesting and maybe almost a bit surprising to a lot of people, is that, you know, when you actually look at it, I think, you know, across all of the agents, I think the team kind of observed that, you know, LM agents struggle to achieve more than 0.15x. Kind of
Mhm.
expert level performance. You guys kind of have a series of tables that kind of summarize, you know, speed up ratio performance and kind of talk about, you know, kind of capability transfer gaps. I think you guys kind of talk about like GPT-5 mini, for instance, achieves like 0.019x expert speed up, whereas like the same system, you know, scores 62.6% on SWE-bench verified. So I guess like maybe just tell us a little bit about kind of like why you think things are so much worse for SWE-efficiency. I think you've already kind of highlighted a little bit of it, but if you had to kind of postulate maybe a few of the key reasons, what would you sort of say?
Yeah, for sure. I think one big one is kind of the tasks feel more long horizon. I think whenever I look at a SWE bench type trajectory, a lot of times it's difficult because a lot of the times when you don't have the criteria that you're evaluating against in your current context. Like an agent has those specific tests that it's tested against already masked out, right? And so a lot of times SWE bench trajectories are you make an edit and then you submit kind of what your best guess at your solving the problem would be, right? You don't have the actual test to check against. For SWE-efficiency, the opposite is true. Basically, we give agents kind of like the exact workload that they're going to be evaluated against, and then all the tests that they need to pass are already in the repository as well. And so kind of agents already have the answer. If you look at some trajectories, basically agents will try one thing, it didn't speed up anything. They'll have to try another thing, they didn't speed up anything. And so the task can get pretty long horizon. I think the way that I view it is that SWE-bench feels like a one attempt in the trajectory versus I think from looking at SWE-efficiency trajectories, we've definitely seen like multiple agent attempts as long as with along with their like multiple tool calls. And so I think that's one big thing that kind of makes SWE-efficiency a little bit harder. I think there's some other things in terms of I think it turns out I think like figuring out to where it make performance changes. I think localization seems much harder. A lot of SWE-bench kind of localizations have, at least from the harnesses I've seen, a lot of them have started to center around kind of like grep as well as like text space file and text space kind of isolation. I think for performance changes, this is slightly different. You might need to do something like figuring out where bottlenecks are on the call stack. Like I think it's possible that like grep based localization tools aren't enough, and so this should be pretty exciting for harness designers or like people who like build harnesses around these language models, just because I think this is something pretty actionable that I think could get performance to improve pretty high on efficiency.
Awesome. And I think one other thing that's really kind of interesting about kind of this project is, at least in the limitation section of the paper, you guys talk about how the focus, at least this time, was on kind of this controlled CPU only setup. But
Mm-hmm.
like maybe potentially some future work could include like scaling to longer running workloads, heterogeneous hardware, things like this. So I guess like that's definitely one avenue of future work. Maybe tell us a little bit about kind of if you had the optimal setup for what SWE efficiency could look like, the optimal setup for performance engineering. You had infinite time and infinite resources. Like, paint us a picture of like what the ideal SWE efficiency would look like.
Yeah, for sure. I think one of the really cool next directions, I think one of my lab mates, Arya, is actually sort of exploring this for the kernel direction. But I think one really big one that the systems folks are interested in is kind of writing software for hardware specific. I think kernels are an example of writing software specifically for GPUs, but kind of you can imagine there's a whole broad space of stuff like writing code for microcontrollers, for example. Anytime someone releases a new microcontroller, you actually do need to write a whole new setup based on the microcontroller's instruction set, at least to achieve the kind of bare metal performance. I think SWE-efficiency, kind of like some way to kind of automate that or automate a code base like rewriting of that, I think would be like a really cool task, and I think that's still kind of like very performance oriented. I think there's a lot of interesting things I'd love to see with like a lot of the language extensions. I think we touched on it briefly in the paper, like extending to like lower level languages. But I think it turns out kind of like a lot of those things, automating a lot of those things is like really difficult. I think for Python, a lot of kind of repos install and build the same. So logistically, it's pretty easy. I think for things like, I don't think Rust has this problem as much, but things for like C and C++, kind of like almost every repository builds differently. And so kind of automating this at scale and even in just like the academic setting is tougher. But it's definitely something I think that would have much more like kind of climbing on that benchmark would yield like much bigger kind of improvements in use cases, especially for the systems community. But yeah, I would love to figure if given unlimited resources, I think those would be the two directions I'd love to flesh out in more detail.
Mm, awesome. And I guess like maybe like now we can kind of step out more broadly into kind of this body of work. Like a lot of people have been working on kind of benchmarks for coding, right? Like as a SWE bench is one, and obviously SWE bench, SWE efficiency is also doing great work. But one also has to wonder whether the benchmarks, and this case the 498, that kind of samples that you guys had, like how do you know whether your benchmark is a good benchmark? So like for instance, like we can set up a benchmark, say for instance benchmark A, and we could evaluate some model on that benchmark, and we could say like, this model isn't great at this benchmark. But like how do you know that the benchmark that you built is like the most representative benchmark for some
Mm-hmm.
end sort of like objective that you're trying to measure? And I'm curious, as somebody that's, built, obviously a really amazing benchmark, I'm sure this is something that you thought a lot about. And how do you like best design the benchmark? Do you think this is, kind of like a user study thing where you have to like talk to actual performance engineers and figure out what great looks like? Like, how do you actually go about like iterating and refining what a great benchmark looks like?
Yeah, for sure. That's a really good question. I think I chatted a ton with Ophir about this as well. So he was a co-author on SWE-bench and also a co-author on SWE-efficiency. One big one, I think it's for sure in the academic community. I think it becomes tough. One big thing is kind of you do want to on your topic of like what makes a benchmark useful. One really easy way to make it useful is usually try and source your tasks from like the real world. Like SWE-bench did an amazing job of sourcing their tasks from actual GitHub issues and actual GitHub unit tests, right? I think for SWE-efficiency, we follow the same approach, kind of like grounding our realism from the fact that these are from actual like real world repositories, like useful repositories too, like pandas, numpy, scipy, kind of like the realism aspect is there. I think that ultimately it is also true that kind of like these benchmarks also need to test like isolated reasoning scenarios. Like I think you could make a super holistic benchmark, but I think the difficulty is like kind of making sure that benchmark reproducibility, there's kind of an anti-correlation with size, where kind of like the more useful and I think the more like holistic and higher quality tasks you will have, I think the smaller the benchmark ends up getting. I think like if you compare like our size, it's SWE-efficiency still has some manual annotation. SWE-bench was like almost fully automated basically. SWE-efficiency had some manual annotation, and then if you look at kind of other benchmarks in the area, I know there's like for example Terminal Bench. Terminal Bench 2 came out recently. Kind of
Mm-hmm.
a lot of those were like manually handwritten and like kind of pretty high quality, right? And so I think there's kind of a trade off that you're making with like how much automation you want to do. And so I think uh, that captures the aspect of like oh, kind of like the realism aspect, right? I think the other difficult part that we're kind of figuring out with benchmarks is that there is some aspect of like if you want the community to use it, you also have to make it reproducible. And then I
Mm-hmm.
think, well, at least with code models, we're getting to the point where a lot of the useful tasks that we'd really want models to do, it's really hard to containerize them, right? I think I was chatting with someone who mentioned that like, oh, they want to use coding agents to maybe manage Kubernetes, but kind
Mm-hmm.
of building a benchmark to do this,
That's very
you
hard.
have to do much more difficult for sure. But
Yeah.
I think the fact that kind of we have to start thinking like that means that these models are getting really, really good. And so I think at some point there's a lot of like really interesting like performance engineering directions we'd love to pull SWE-efficiency in. But I think kind of balancing that trade-off is tough, especially in academia as well.
Mm-hmm. Yeah, and I think one thing that obviously is like a large part about of kind of benchmark creation, I think one thing you guys talk about is kind of data collection. And I think you guys kind of had this like multi-stage pipeline, and I want to say you guys had like keyword filtering, static analysis, like coverage tooling, execution validation. And the goal at the end of the day was to like extract these like realistic optimization tasks from GitHub PRs. The thing is like with every single benchmark that anybody wants to create, ultimately you need to collect data because it is a benchmark. And I'm curious, like, do you think that, I mean, from, your knowledge and maybe, Ophir's as well, seeing as how he was involved with SweBench, like, what do you think are some of like kind of the common challenges people run into when they're trying to collect data? Like, is there a lot of noisy data, especially considering maybe not every GitHub PR, has great code, especially if a lot of it is starting to get more and more vibe coded? Like, how do you sort of like do like good quality checks?
Yeah, for sure. Yeah, so I can touch a little bit kind of like how we did it. One big design decision that we wanted to make with SWE-efficiency is like kind of we started with around 100,000 raw PRs
Mm-hmm.
from kind of the 11 or 12 repos we scraped. And kind of once we got down to the annotation stage where we wrote kind of like the performance workloads to annotate with each one based on the PR content, we were around like 1,000. So this is like roughly like 100x decrease. And I think
Mm-hmm.
one of the big things like with the scalability is like we wanted to kind of build data set pipeline stages that we're pretty confident completely remove things that we don't care about, and then also are pretty confident that actually still retain things we care about. So in our case, kind of when we inverted this like contributes test PR criteria from SWE-bench, one thing that actually introduced into the mix is that we actually started selecting PRs in an early stage on like things like doc string changes, things that don't
Mm-hmm.
contribute tests, but like this happens to correlate with people just making comment changes or something, right? And
Mm-hmm.
so then kind of like with that lesson, then you need to build another data set pipeline to like kind of maybe check the syntax tree and make sure that kind of these changes actually do change the code base in a meaningful way. And kind of like basically designing each stage to carefully kind of like remove noise is definitely a tricky thing. It's pretty high touch. I would love to see if like eventually you build some like meta benchmark if a language model can do this. But it seems like it's pretty high touch and like depends really a lot on the problem domain. Our lab has like a similar related work or kind of a work in a different domain on like kind of evaluating agents for computer architecture on like Q&A questions.
Mm-hmm.
And kind of for their domain, it's very hard to source like super high quality implementation tasks for computer architecture. There's already a lot of it in the community, like Verilog Bench and like all these others,
Hmm.
but kind of there's some subsets of computer architecture knowledge that aren't well covered, and so Q&A kind of covers all of them. But they build like a super intricate pipeline to actually generate these things at scale. And so I think it definitely really feels like it depends on the domain. I know there's so many other benchmarks domain specific that kind of are super high touch, and so I think it's something that like is you kind of do need to understand the domain well to build it, but it'd be really cool in the future if it could be automated as well.
Hmm. Awesome. And kind of zooming out more broadly, in kind of, I guess, the next few years of your PhD as you finish up, um, do you want to continue to work on AI for code? And like kind of you kind of have hinted that, this is maybe like a really interesting kind of like focus and maybe one of the key focuses for the rest of your PhD. This is a very sort of, fast evolving field, and I'm sure that there's a lot of really exciting follow-on work that can go on, not just in, performance engineering, but kind of as you hinted at, other sort of infrastructure kind of challenges, Kubernetes, so on and so forth, that people haven't quite evaluated with like coding agents quite yet. Like, what are you really excited about kind of in the next few years?
Yeah, for sure. I think I'm definitely just most excited about kind of like closing this self-improvement loop. I
Mm-hmm.
think we've gotten these models to be so good. Hopefully, it'd be super cool if one day they could just reason about their own compute efficiency, and then
Mm-hmm.
you kind of really close the loop
Right.
in terms of like how do I improve the model, and then the model will improve its own infrastructure, and then that infrastructure helps the model train faster, and you kind of
Mm-hmm.
like get this self-improving loop.
Mm-hmm.
Um, I think that that kind of informs a lot of the things that I'd like to work on. So like performance engineering or just like compute scalability.
Mm-hmm.
I'm super interested also kind of, I've gone more interested in kind of like the actual software side of things. I think
Mm-hmm.
one thing with SWE-efficiency that we kind of realize is that it's possible kind of like the way that we organize GitHub repos or even just do like version control right
Mm-hmm.
now is super well designed for like a maybe human software engineer, but kind of the workloads that we want to start throwing at code bases, like imagine running like 100,000 Claude code instances on one code base.
Mm-hmm.
I think kind of context management, making sure things don't like blow each other up, I think becomes a very hairy problem. And I think there's a really big cool opportunity to maybe reevaluate how we kind of organize software to kind of account for this. But yeah, I think those are kind of like the big spaces that I'd love to like sink my teeth more into.
Awesome. Maybe our last question here, like kind of like from an industry standpoint, there are a lot of different labs that are working on kind of AI for code. There's a lot of different approaches to this. There's some that are doing kind of an AI for math kind of symbolic approach to this. There are some that are obviously, like Claude, so on and so forth, that are taking other approaches. There's some that are taking kind of like RL approaches. Like there's a lot of different kind of approaches to this. And obviously there's a lot of different benchmarks that are going on kind of like at a high level, when you think about kind of AI for code as a field, what do you think might potentially make, a winner in this field? Like, what do you kind of think is making someone successful and actually like building these models? Because obviously, like, we're kind of, we've talked a lot kind of on the other side of like, okay, we have these models and, they've been built. Now, how do we kind of see how well they do on SWE-efficiency or how well are they doing on SWE-bench? And we've also talked a little bit about how, we noticed like some of like the better models are going like 0.15x. Like, what do you kind of concretely think? Like, if you were, tomorrow, say you were in charge of building all the models, what would you do differently?
Yeah, for sure. That's a really good question. I think so. I'll give an answer that's kind of biased. I think by kind of our lab's focus. I think my advisor VJ is super into kind of just co-design in general. I
Mm-hmm.
think that's one big thing that we're starting to see is kind of like a lot of these, maybe like some of the applied labs like Cursor when they're like starting to train their own models. I think kind of co-designing the task with your model seems to kind of really help with things. Like I've been using Composer for a lot of my stuff and
Mm-hmm.
anecdotally like really good stuff.
Mm-hmm.
I think just in general at least for the models that kind of we see do well on efficiency, I think in my mind I have some kind of prior that it kind of relates for the fact that like at least for kind of efficiency, I think one of the ways to do well on it for a model is like kind of be really good at dealing with consistent feedback. And it seems like kind of the models that perform well, kind of like one really big, cool, surprising result was like seeing how well Qwen 3 Coder did on our benchmark, right?
Mm-hmm.
And so I think they had like a really big focus on kind of incorporating that into their like Coder CLI tool. I think Codex from OpenAI, Claude Code from Anthropic. I think kind of it seems like some of that correlates with like kind of our benchmark performance. And so I think being able to deal with like feedback directed like code optimization or just dealing with feedback better, I think it's like kind of a really good way of like doing better on like maybe these benchmarks and also on the actual useful tasks. Just because I think there are definitely a space of problems. I think SWE-efficiency is showing one of them, but there definitely a space of problems where you can't reason about software just by looking at the code anymore. I think you need to run some snippets. You do need to figure out how they interact with the hardware, and then with that, kind of figure out how do you actually improve on the task. And so I think kind of like feedback, like focusing on like feedback driven optimization is like probably a really cool next direction. And I think probably a way to get these models kind of a lot better at these like systems, like core systems reasoning tasks.
Awesome. Well, on that note, thank you so much for coming on the podcast.
For sure. Thank you so much for having me.